Good evening, everyone. Am I audible?
Yes, you are audible.
So, before beginning with today's class, is there any doubt regarding the previous classes or anything in particular which you want me to address?
Yes, sir. I have doubt regarding assignment, week 4 assignment.
Okay, what doubt do you have?
Actually, in part B, there is one question regarding the simulation for acetone, ethanol, and other mixture fluid property generation. Actually, I am using the rest of property, but while the answering, what I'm getting, it is based on the NRTL method. But in method system, it is showing rest of property as well for that component.
So, is the week 4 assignment date over?
Yes, sir. Answer is already getting out.
Then you can share your screen and show me the question once.
Actually, sir, I'm right now traveling. I'm connecting to mobile.
Okay. So,
It's a water ethanol mixture.
wait, let me see if I can get access of the question that you're referring to.
Sir, same is my concern. We have done the simulation and
Can
got
you
different.
can you share your screen? As in, I just wanted to see the question that
Sir,
you.
I can share you in 10 minutes, sir.
Okay.
Till then, sir, I'm also joined, switched on my laptop. I will share you in my screen after 10 minutes.
Then let me see if I can get hold of the question. Week 4.
Yes, sir.
Okay. So which question is this? Question number? This
Part
one.
B.
Part B.
This one. Yes, yes, yes.
An equimolar feed mixture of water, ethanol, and acetone, total 3 kilomole per hour at 90 degrees Celsius and 5 atm, is flashed at 35 degrees Celsius and atmospheric pressure. Create a new property set containing enthalpy, fugacity coefficient, and internal energy all in mixture and answer the following. Okay, so what is the problem that you are facing?
Actually, I am use the RefCop property package, and answer is getting in the correct answer is from NRTL package. We are cross check as well. But in RefCop property, in method assistant, RefCop property, I think it's already also suitable for this kind of mixture.
Okay, so you have chosen a property method that you have that
RefCop,
is from the reference property method, as in from the method assistant you have chosen, while the correct answer is given with basis of in RTL.
it's correct, sir. And
Okay.
RefCop property package, these three components are already enlisted in help guide as well.
So why did you use ref prop? As in, what is the property that you have used?
RefCop, sir.
Ref prop.
Yes.
So all the answers that you have that are given are here are based on NRTL.
Yes, exactly, sir. As per NRTL, all the given answer is correct, but in depth of slightly this are we are getting.
But over here you can see that it is telling that for refrigerants use ref prop. The
But in detailed discussion, this retro property method in last row, uh, these three compounds are already listed in this method, retro.
I am not able to understand this point that you are trying to tell me.
So wait, sir. I will share your screen in 2 minutes, sir. Then I will tell you. Out of the five, we are getting two wrong answers, and three are right.
Let me see by trying it with Wilson.
Yes, yes. In this window,
This window.
uh, yes, in retro property method, please select last one, sir.
This is week 4 assignment. Temperature is 90 degrees Celsius and pressure is 5 atmosphere. And the mole flow is 3 kilomole per hour is the total mole flow, and it is equimolar. Now we have to specify the flash. It is flashed at 35 degrees Celsius and atmospheric pressure. 35 degrees Celsius and 1 atmosphere. The heat duty. So this is the heat duty that you are getting. So
Yes, sir. 5.38.
so the heat duty range is given minus 6.1 and 5.8 between these two values. So you are getting the heat duty within that value only.
Yes, but by choosing RevPro property, we are getting minus 5.38. In RevPro property method assistant, these three components, water, ethanol, acetone, already mentioned in RevPro property method assistant. So why we can't use this method as well?
First of all, when we were looking at the method assistant over here, it is telling that for refrigerants use RefProp. So if the process is not any refrigeration process, then like we should not be using this RefProp property method. Over here it is being said specifically that for refrigerants use RefProp. The first line it is telling that use an activity coefficient method such as NRTL, Wilson, Uniquac and or Unifac method.
Okay, even though this RevPro property method enlisted these three
Listen, like if whenever
components,
like
refrigerant
whenever
process.
yes, like whenever you are trying to select a particular property method, you should always have the proper knowledge of the system that you are dealing with. Like in the question, it is not telling that any refrigeration process is taking place or not, right? Or if any component is used as a refrigerant. Now, whenever we are choosing any property method, you will see that most of the examples that are dealt in search video or even in the problems that we are solving, either the property method is specified to us or out of these four property methods, any one property method is being used. Okay. Until and unless any specific process is taking place. Now, if the question had said that this method, this process is a refrigeration process, or any component that is being used in this process acts as a refrigerant, only then you should have gone for this property method, that is refprop method. Else you shouldn't use the refprop method. The very first line it is telling that use an activity coefficient method such as NRTL, Wilson, Uniquac or Unifac. Now this is The first line is given with the basis that you don't have any extra specification for the process that you are handling at hand. So this is a widely accepted property methods that they are listing at the very first line. Okay. Now you can see that with NRTL you are getting the answers. The other thing that we can check whether Wilson, Uniquac or Unifac are given close answers or not. But since the question is not telling that you are using any refrigerants or anything, you shouldn't use ref prop method. Because in the second line it is specifically said that for refrigerants use ref prop. Else we can use all these methods. Are you getting what I'm trying to say?
But
Hello?
they write these three components in property method.
Three components in the ref prop property method, like what you were trying to say, I am not able to understand this point clearly.
In repro property method, these
Huh?
three components are well, uh, no, sorry, in method assistant page.
Huh? In method assistant, yes,
Yes, yes, just yes. In last, please select repro property method. Sir.
this
Last
one.
one.
Okay,
Yes, yes. In this scroll down, sir. In
scroll down.
bottom,
Huh?
there is a mention. Yes. In here, all three components are enlisted: water, ethanol, and acetone. Water is a pure liquid.
It's based on the most accurate.
Please scroll down, sir, later as well.
Yes, I can understand what you're trying to say. Over
Component are
here,
enlisted.
the fluid models and available properties you are trying to say, right?
And all three components are enlisted. Water, ethanol, and acetone. This water is a pure fluid as well.
But the main issue, like, as in the reason why I am telling you this is like you don't know whether the process is used as a refrigeration process or not, right? That is what my concern is. The property, yeah, what you are telling, that I can understand, like as in ref prop property method, like all the components are being listed, then why can't we use this property method? Now every thermodynamic property is suitable for particular processes that we are trying to address. But if your process is not that of a refrigeration process, then why should we use a thermodynamic property that is suitable for refrigeration process? If your question said that it is a refrigeration process, then you could have used that. I'm trying to understand what I'm like
Okay, okay,
conveying.
got it, sir. Got it. And one more question. In actually, I am right as a hydrocarbons in assignment
Okay.
4, and the answer is hydrocarbon. So for that, the answer is getting incorrect. Incorrect.
Or like without using the plural form.
Yes. First question, the very first question.
First
I
question.
write as a hydrocarbons. Yeah.
So you have to be like specific since look at the word that they're using over here. They're using uses, right? So with
But the second word, a trace amount of hydrocarbons, the same thing, the same word, hydrocarbon. Actually, the first word, actually, by the grammatically, first the answer is hydrocarbon and the trace amount of hydrocarbons. These two words already mentioned in PPT as well. Means in classes, recorded lecture.
so over there, sir has used hydrocarbons.
In first, in first uses hydrocarbon solubility model and for the calculation of trace amount of hydrocarbons in the drinking water.
So you can address this. You can like mail it to the NPTEL people with
Yeah,
the
yeah. Okay,
appropriate screenshot.
okay, okay. Got it.
Because with in the first blank it should be hydrocarbon and not hydrocarbons.
Yeah, yes, yes, I understood.
For the second blank, you can address it to the
Hydrocarbons.
yes, yes.
Okay, okay. My side.
So with Wilson, is the results coming fine?
Sir, when I use NATL property method, the answer is getting right, sir.
Yes, we were discussing about that only. So what is the problem that you are having?
No, no, sir, no problem.
Sir, I'm unable to install this Aspen Plus software.
What problem are you facing?
It is showing me that the installation couldn't locate the setup files.
Then you have to like the installation files that you are downloading. You should keep it in a directory and you need to install the Aspen in the same directory as well.
Yes, I've given a location where my file have to be downloaded and all. I'm
Hmm.
coming to the last step. Few files are being downloaded, sir, and for the few things, I mean, for the few softwares, it is showing that I'll just read a pop-up message that had been shown on my screen, sir. One or more of the selected features are requiring a Microsoft Visual C++. Now,
Hmm.
however, the installation could not locate the setup kit anywhere under my given location path. So, and that installation has been stopped there, sir.
Then
I've been
the
trying this multiple times, but the same thing is happening.
then you have to install that Microsoft C++ file.
Okay, I,
Install it first and then try to install the software. I think the error will be solved.
in the same way, I'm getting a 7 different pop-up messages so that I have to install all those software separately and then I have to do this, sir.
Yes, those are few prerequisite softwares are required in for running the Aspen because it does have some built-in coding features. For that, I think few softwares are needed. Those are prerequisites to install the software.
Okay, sir. Thank you.
Any more doubts?
Hello, sir.
Yes.
I wanted to ask about how you were able to find out the fugacity coefficient for week 4 assignment.
Fugacity coefficient for week 4 assignment.
Yes, because when I was scrolling through the properties, I couldn't find the symbol for fugacity coefficient.
Which question is it?
Number 10. 10.
The fugacity coefficient of ethanol in feed mixture. So
Yes.
is there anyone who has solved this question? Kindly help him out. We have discussed these questions, I think.
So I can share my screen, but my figurativity answer is coming wrong, but I can share my screen.
Yes, show him how you have calculated. I think you have to use NRTL, Wilson, or all those property methods to get the right answer.
Sir, that's I have used different method. I use idle. That's why my answer is coming wrong. I know that, but I can share the screen.
Share the screen and show him.
My screen is coming.
Yes, yes, it is visible.
So see, these are the properties I have defined over here in the simulation. See, and these are the stream results, and one minute, sir, I'm showing. So it's got hang. My Aspen is getting hang.
Okay, let me try it from my end.
But it is totally given in lecture number, as a lecture of 4th week. Sir has defined the property and has shown me. It got hang my.
So through add properties, you are adding
Yes,
fugacity
yes,
coefficient.
we have to add the what are the different things they have asked to do. I have added it and different. They have shown. I don't have to install all the properties. I have to add in the property fugacity.
Okay. So you can stop sharing your screen. So to add this fugacity coefficient, you need to follow these steps. So kindly look at this demonstration. So the components that are given to us are water, ethanol. I hope my screen is visible to everyone, and acetone. Next, we have to choose a property method. The property method is not given. From the discussion which we had just now, it is always better to go with the simplest suggestions that are given by Aspen. So since our system is not at a high pressure, we are going to select no. And the very first suggestions that are given to us are NRTL, Wilson, Uniquac, and Unifac. So give the priority along the like in the order in which these property methods are mentioned. So let us go with NRTL only. So we are clicking on next. So you can see all the interaction parameters of water, acetone and ethanol system are being updated from the source that is mentioned over here. So we are going to click on next. We are going to run the property analysis or setup. Next we have to come to the simulation. Now coming to separators, we are going to select a flash tank.
Sir, can you please share your screen?
Is my screen not visible?
No, sir.
Now it is.
So this is the flashing process that has been asked in the question. Next is we need to specify the feed stream that is coming in. So the feed stream is coming at a temperature of 90 degrees Celsius and 5 atmosphere. So over here this is 90 and this is 5 atmosphere, and the mole flow is equimolar. It is set at 3 kilomole per hour. So 3 kilomole per hour, and since it is a equimolar, so 1 kilomole per hour each. Now we are going to click on next. Over here the block specifications are being asked. So it is flashed at 35 degrees Celsius and atmospheric pressure. So we are going to specify this as 35 degrees Celsius and the pressure is 1 atmosphere. Now it is telling that the required input is complete. Now we are going to click on next and we are going to run the simulation. Now coming to the results over here, this is the result for the flash. So over here a negative sign is coming. I hope you can understand why, because the feed stream is at 90 degrees Celsius while the product streams are at a lower temperature. So cooling process is taking place, and if you convert it into kilowatt, this is minus 5.97642 kilowatts. Now coming to the stream results over here, these are the stream results. Now over here you can select add properties. So what are the properties that are being asked? You have to, over here it is asked the fugacity coefficient of ethanol. So fugacity coefficient. What is asked? The fugacity coefficient of ethanol in feed mixture. So here it is given fugacity coefficient of component in mixture. We are going to select this. Okay. Anything else? Enthalpy of liquid output mixture, internal energy. Let us select internal energy. What is being asked? Internal energy of the feed mixture. So internal energy mixture is selected over here, and rest enthalpy. And enthalpy of the mixture is required. Now let us click on OK. So all of these values are given now. This is the fugacity coefficient. So fugacity coefficient of ethanol. So fugacity is 0.338. So this is the range that was given, 0.31 and 0.35. So this is the value that you are going to get for the fugacity coefficient of ethanol in the feed mixture. So is there any doubt regarding this? Someone had asked this question.
No, sir. Thank you.
Okay. Yes, Shiva. You can unmute yourself and ask.
Hello.
Yes.
Sir, I have one question. Sir, in previous question you have said that we have used an
I cannot
RTL.
understand what you are saying. There is too much of background noise. Hmm. Yes.
Hello.
Yes, yes, I can hear you now.
Uh, Sir, in previous question you have said the we have used an RTL Wilson and all the method we have used, and this is a good method, and we have to take the result accordingly. Then, sir, what is the best method we have considered for that?
So for that case, I had actually discussed this question in the, I think in the first week or the second week. So as in which method should we use if there are multiple options? So for that we need to do data regression. If you check the week 1 or week 2 lecture over there, I have said that if we do data regression and we actually check which method has the best fit among the selected property methods that you are, that options that are given to you. The method that gives the lowest RMSC is the method that you should go with.
Okay, sir. And it means that whatever value of the lower RMS value, then it will be best method.
Yes, yes.
Okay, sir. That's why we have used an RTL for the previous question.
Usually the property methods either they are mentioned in the question, but if you don't have the property methods mentioned and you are confused as in which property method you should use, then you should perform data regression and find out which property method gives you the least root mean square error, and then go ahead with that property method. Now root mean square error with respect to what values? The experimental values. Okay. So the last class we were trying to solve this problem, like we have to estimate all the physical properties of a component for which no data is available in the base of the simulator. So this was an MTB molecular formula of MTB. So over there, the problem that we faced were that we were not able to get the mole file of MTB. So for this, how to do, there are two ways to do it. So first, if we just give a component id x, and because this component id is not there in the data bank, you are not going to get any component name or alias or the cas number for this component, since you are going to define it. So now you are going to select user define, and over here in the user defined interface you can give an alias, like I'm giving my name over here, and then I'm going to click on next. So there are two ways how you can do it. One is we can draw, import or edit structure, or we define by its connectivity. So if we have to define a molecule by its connectivity, what we usually do is, if you can see the screen over here, we have numbered the carbon atoms from 1, 2, 3, 4 and 5, and the non-hydrogen atoms that it is linked to, that is oxygen. So if the atoms numbers are numbered, if the components are numbered, then 1, 2 and 3 are carbon atoms, 4 is an oxygen atom, and 5 is also a carbon atom. So now let us define this structure. So if I define them, if it by its collectivity, it is said that atom 1 number. Okay, so this is 1. So what is the atom type? It is a carbon. Okay, atom 2 number is 2. And what is the carbon atom number? It is also a carbon. And what is the bond type? It is a single bond. So how did I do it? This is carbon 1, this is carbon 2, and I have defined this structure C dash C. Only this part I have defined as of now. Okay, now over here it is telling that next we are going to define this part, that is this 2 is connected to this carbon which is numbered as 3. So this is carbon, so this is connected to the third atom which is also a carbon, and that is a single bond. Now over here a chain is being formed. Now this 2 carbon is connected to fifth carbon over here, which is the fifth atom in this chain. So what we are going to do, so this is also 2, this is carbon, so this is carbon atom number 5, this is also a carbon, and this is also connected by a single bond over here. Next we have to define this part, that is the third carbon atom is linked to the number 4 oxygen atom. So we are going to select 3 over here. Since we have defined third atom as carbon, you see that I did not have to like select anything from here, it got auto updated. This is going to atom number 4, and what is the atom type? This is an oxygen, and this is also connected by a single bond. Okay, now this is being done. Now we are going to close this, so you can see that the structure form was opened. Okay, it is better that if we give the molecular weights and all the normal boiling point, specific gravity, the data that we have for the compound, if we have it, then we should give it over here. Since we don't have it, we are going to make Aspen do the calculation. So we are going to click on next. So there are two options which are usually given. You can see that the NIST TDE data is being disabled because we did not provide the inputs previously. All the molecular data, all the molecular weight and the data that was required over here, since we have left it blank, this NIST TDE option is deactivated now. So what we are going to do, we are going to estimate using Aspen property estimation system, and we are going to click on finish. Saving the data you entered, we are going to click on OK. Now we are going to click on next. Let us select the property method. We are going to select NRTL property method. Now let us go to next, and we are going to run the property analysis. It is telling that the following conventional components are not in a data bank. So it is obvious because we have not taken it from the data bank itself. So now if we click on review, So here the pure component data are given to us. So these are all are estimated from the molecular structure that we have provided initially. Okay. So if you come over here, then the molecular weight, then the boiling point, the critical temperature, the critical pressure, all are given from based on only from the molecular structure that we have given. And you can see that from where are these values are retrieved, they are retrieved through this RPCAS system. That is, if you remember, then this RPCAS is actually a regression correlation model which is used for estimating the properties or the parameters of a pure component through regression. So from there they have calculated all this data. There is another way to do this, and how we can do it is, if we go to components, we go to user defined, we are going to keep this part as same. Naturally we don't have the values for these parameters over here. We can draw import the structure. For that we need to go to NIST chemistry webbook. That is, we have to download the mole file for this particular component. So over here you can search. So what is the, we are searching for MTBE. So if I click on enter, so you can see that the MTBE is generated. The 2D mole file is also available. So we can download the 2D mole file on the desktop. Now how to upload it? We have to come to Aspen. Over here it is telling draw / import or edit structure. So from here you can import mole file, can come to the desktop. You can see that the mole file is available over here and you can click on open. So once you open the mole file, you will get the structure over here. If you see the structure that is given over here and the structure that is given over here, the molecular formula for both the structures are the same. Once this is done, you can close it. It is said that the structure is available. Now you can click on next. Over here, since I have given the mole file, you can see that it is given this evaluate using NIST-TD. Now we are going to select evaluate now. Now we are going to click on OK. We are going to click on OK. So these are all the values that are being retrieved from the NIST-TD. If you remember that the molecular weight that we had obtained from just giving the molecular structure previously, it was around 74 to 77 kg per kilomole. But over here you can see it is 88.15. This becomes more precise by using a mole file. If you check this data bank over here, you can see that this value is close to the value that we have got in Aspen. Okay. Then the heat capacity results are also given over here, and this is the molecular weight. Now these are the parameters that are retrieved from the NIST. Over here it is the predicted values, and these are the evaluated results. Is there any doubt? Is there any doubt regarding this problem?
No, sir.
Now we are going to solve a few more questions using this property analysis, as in we are going to do some pure property analysis, binary analysis, and tertiary analysis as well. So these are the few questions that we are going to solve. So we have to find the density of acetone at atmospheric pressure at 25 degrees Celsius and 75 degrees Celsius. We are going to use the NRTL property method, and the valid phases are liquid and vapor. Okay. So you also try it on your own and try to give me the answer that we are getting at these two temperatures. And then I am also trying to solve from my end. We are going to compare the answers that we are getting. It will be better if you take the screenshot of this entire set of problems. We are going to solve them one by one. So the component is acetone. What is the property method that we have to use? We have to use NRTL property method. Next, we have to do pure analysis. So what is the property type? Thermodynamic. So what property are we going to analyze? We are going to analyze density. So density is over here, density of pure compound. We are going to set the unit as kilomole per cubic meter, and the temperature it is being asked at 25 and 75 degrees Celsius. Now there are two ways which we can do, that is equidistant, that is we can see the variation of the density across a temperature, or we can just give the specific values of the temperature that we want to calculate. So if we want to see list of values, then the temperature is 25 degrees Celsius and then 75 degrees Celsius. The component that we are going to do is acetone. Now, the pressure is 1.0235 bar. It is being said that we have to do it at atmospheric pressure. So we are going to set the pressure as 1 atmospheres. Next, we are going to run the analysis. So over here, so this is the variation of density with respect to temperature. So this is at 25 degrees Celsius. This is the density of acetone, that is 13.527. It is given in kilomole. We change it to kg per cubic meter. So this is the density of acetone at 25 degrees Celsius, which is roughly 786 kg per cubic meter, and this is at 75 degrees Celsius. Now let's say if instead of this list of values we want equidistant, so if we start it from 25 degrees Celsius and we want 75, and with an increment of 5 degrees Celsius, and we are going to run the analysis now. So this is for a range of values. We are going to get the same trend, but we are going to get different values at different temperatures for acetone. Is there any doubt in this problem? It is a very straightforward problem. This is for a pure component analysis. So try to do this problem where you have to find the specific heat capacity of water for the three phases, solid, liquid, and vapor phase. And this is the temperature range which is given to us. This is also a straightforward problem, but the inference of this problem will be a bit different. Let us come to components. Let us add water over here. Let's go to next. Let us run. Now coming to the pure component analysis. Over here, the property method, previously we did density. Now we have to do specific heat capacity of water. So what is specific heat capacity? This is constant pressure capacity for a pure component. Now the pressure is constant since it is said that we have to find the specific heat capacity at atmospheric pressure. So we are going to select Cp over here. The unit is going to be, let us keep it as joule per kg Kelvin. Over here, phases are being asked. So the valid phases for water is, that is the three valid phases are solid, liquid, and vapor. So we are going to select all the three phases. Next, what we have to do is we have to specify the temperature range, that is -50 and 150. So the starting point is -50 degrees Celsius and this is 150, and let this temperature be 20. So there is an increment of 10 degrees Celsius. The selected component is water only. Now we are going to run the analysis. Now the thing that we have to see is, like, for water only this much, that is in liquid phase, that is from 0 degree to 100 degree. This is the variation of the Cp of water with respect to temperature. Similarly, for vapor, that is the violet line, only from 100 degrees to 150 degree, because from 100 degree and onwards the water exists in the vapor phase. And for solid, similarly, it will be from -50 up till 0 degree. And the rest of this part is not of any use to us, because only up till this much water exists in the solid phase. Is there any doubt in this question? Is there any doubt?
No, sir.
Try to solve this third question. Take 5 minutes of time. We have to find the Gibbs free energy of pure ethanol at equilibrium condition within the temperature range of 0 to 500 degrees Celsius, and you have to add two different pressures, that is at 1 bar and at 20 bar. You have to find the Gibbs free energy of pure ethanol. Take 5 minutes of time and try to solve this problem. So has anyone solved this problem? Hello?
Sir, I couldn't do with two different pressures.
Okay. So let us see for pure ethanol. We have added the component. Now we are going to click on next. The interaction parameters are updated. Now we are going for pure analysis. Now the property type that we are going to go is for it is here free energy for a pure component. I think this is the gives free energy. Does anyone have any doubt?
Sir, how to assert an equilibrium condition?
Assert as in
How to specify the system that we need equilibrium condition?
how to specify the system. As in whenever we are specifying this conditions that are being asked, all these conditions are being calculated in equilibrium only. You don't have to specifically mention whether you have to do it in equilibrium or not.
Okay.
Unit be joule per kilomole. This is 0 to 500 degrees Celsius, and we are doing it for ethanol. So two pressures are being asked. So one is at 1 bar. So we have to specify this as 1 bar first, and then we have to run the analysis. This is for 1 bar. Next, we have to do it for 20 bar. And then we have to run the analysis. This is for 20 bar. Or we can do one thing. This is for 20 bar. We are going to go to home. We are going to select another pure component. Every time we select an analysis, you can see that these numbers are getting updated. So this PO3 is for 20 bar. Okay. You were asking if how to do it for two different pressures. So you just need to perform another pure analysis. Then this number is going to get increased. So this is PO4 now. We are going to keep it as joule per kilomole. The temperature range is given to us as 0 to 500 degrees Celsius. And we are going to keep the number of intervals same. We are going to select ethanol. And now this is for 1 bar. We are running the analysis. So the PO4 G plot is being updated. What we are going to do is we are going to merge the plot with whose PO3 G plot, because this is for 20 bar and this is for 1 bar. So we are going to merge both the graphs. Now what we are going to do,
And sir, don't we need to bother about the phase the way we did in the case of water? We
In the
don't know. Hmm.
in water, we were asked to find out for the different phases. Now, since no different phases are mentioned in this problem, we are keeping it to liquid only.
So at 500 degrees Celsius, it would be in vapor phase, right?
Okay,
At 1 bar.
you select the vapor phase also. What you are saying is right. So we are selecting vapor phase, liquid and vapor phase of ethanol. So this is for 1 bar. So this is the vapor phase of ethanol and this is the liquid phase of ethanol. The gives free energy of mixing. Next, let me see if I can merge the two graphs at two different pressures. Don't know if will happen or not. I think the Aspen updates its calculation as we change the conditions over here. And this is for 20 bar and the component is ethanol. We run the analysis. Yes. You can find out at different pressures, but you cannot find out as in for you cannot compare both the results at different pressures. That is one problem that is there. You can do it in a different platform. Let's say you can retrieve the data and do it in Excel, but not over here in Aspen, because as you can see, as I have updated the pressure to 20 bar, the previous results that were there, they have vanished, as in since the calculation was being updated. So I hope it is clear as to how to do this. So if you click on OK, the results are available. You can come to the results and you can get the data from here. So what you can do is you can copy this data. You can go to Excel and plot it for the variation of the gives free energy at different pressure, and you can visualize through Excel. Is there any doubt in this particular simulation?
No, sir.
Now over here, there are two problems. I think we have done this problems previously also. So we have to find out the pressure temperature envelope for pure benzene, pure toluene and pure water at 1 bar pressure, and we have to use the NRTL property method, and then we have to merge the plots. So try this problem on your own. This problem 5, 4 and 5. Merging the plots is actually enables us to visualize the change in a much better way. Now over here we are going to generate the pressure temperature envelope. So what is the pressure temperature envelope? We are going to obtain the pressure temperature envelope of pure benzene, pure toluene and pure water. So first is pure benzene. So I'm going to keep the mole flow at 1 kilomole per hour. Valid phases are vapor and liquid. The pressure is at 1 bar, and the method so over here it is a vapor liquid system, so we are going to use the standard method over here. So it is telling that the standard method is used by default, so we are not going to mention any method over here. So over here this is, we are doing it for benzene. We are going to run the analysis. So this is the PT envelope for benzene. So can anyone can you tell me what is the bubble point or the bubble point temperature of benzene at 1 atmospheric pressure? From this graph over here.
~80 degrees Celsius.
And what is the critical temperature?
287, I guess.
Yes, it is between 285 and 290. So for similarly, what we are going to do is we are going to do it for another, that is for water. We are going to keep the mole flow as 1 and the pressure we are going to set at 1 bar, and then we are going to run the analysis. So this is for water that we have. So if you see over here that the temperature is 99.649. Why a reduced temperature is shown? Because we have not exactly specified the temperature as 1 atmosphere. So if we want to specify this temperature, if I specify this temperature as instead of 1 bar, and if I specify it as 1 atmosphere, and then I run the analysis, we are going to get the temperature as 100 degrees Celsius over here. And next is over here, what we have to do is similarly we have to do it for pure toluene. So we are doing it for pure toluene. We are keeping the pressure as 1 bar and then we are running the analysis. So this is for the pure toluene. Okay. Now the next question, it says that we have to obtain the PT envelopes for ethane pentane mixture at 1:1 and 1:3 ratio, and we have to use Penn-Robinson method.
Sir, we have to merge the plots in question number 4.
Sure. So here, how you can merge the two plots. I have deleted one plot also. Let me add that as well. This PT envelope, H2 envelope of water and pink. This is for water, and toluene. Benzene is left. So I'm setting this as 1 bar. I'm running the analysis. This is envelope 4. These two are merged. Now I'm merging it with envelope 4. So 3 are merged. So what we are going to do is we are going to do it in a single y-axis. So this is how you can merge the 3 graphs. Okay. Now the pink one is, can I change the legend? This is for water. This is for toluene. And this is for benzene. Is there any doubt?
No, sir.
Now the last one is we have to obtain the PT envelope for ethane pentane mixture at 1:1 ratio and 1:3 ratio. And we have to use Penn-Robinson method. So try to do this. Previously in the mole flow, we used to specify 1. Over here, you just need to specify 2 different mole flows for the ethane and pentane components. But before beginning this simulation, you need to add the components in the component list, and you have to change the property method from NRTL to Penn-Robinson. The rest, all the processes are same. Next, what you have to do is you have to add this ethane and pentane. You have to change this property method from NRTL to Penn Robinson. Now what we have to do is we have to specify the flow rate. First is ethane pentane is 1:1. So here we have ethane, we have pentane. We are going to delete this and we are going to keep the pressure at 1 bar and we are going to one pentane one. One is equimolar mixture of ethane and pentane. So we have set the molar flow rates at 1 kilomole per hour each. Now we are going to run the analysis. So this is for ethane and pentane for vapor fraction 1. So this is the bubble point curve and while this is the dew point curve. Okay, next what we are going to do is we are going to do another PT envelope analysis. For this case what we are going to do, the ethane pentane mixture is 1:3 ratio. So this is 1 and this is 3. We are going to set the pressure as 1 bar only and then we are again going to run the analysis. So this is for 1:3. So let me write, just make the legends a bit different. This is 1:3 and now let me merge the plots. So this is for 1:1. Y-axis, we are going to have a single y-axis. So this is how the curves look like. So is there any doubt in this problem?
No, sir.
Now we are going to do some ternary analysis. Like all the questions, they are almost similar to each other. So I'm going to show only one. So what we are going to do is we are going to do the sixth question. So what ethanol, water and ethyl acetate system, we have to find out the residual curves at 1 atmosphere pressure. The valid phases are vapor and liquid. We have to use NRTL property method and we are going to draw 10 to 15 curves for this ternary analysis. Okay, so let us start. So what are the components are there? We have ethanol, water and ethyl acetate. So ethanol, water and ethyl acetate. The property method that we have is NRTL property method. Next is we have to do ternary analysis. So we are going to select ternary maps from here. So let me select this, continue to ternary diagrams. So what is being asked? It is being asked that we are going to do it at 1 atmospheric pressure. The valid phases are vapor and liquid and 10 to 15 curves. So over here we are going to change it to vapor, liquid, liquid. In RTL method, the pressure is 1 atmosphere and the number of tile lines is, let me set it to 15. Now what we are going to do is we are going to run the analysis over here. So over here you are going to get all the details of the tile lines. That is, there are a total of 15 tile lines and there are a total of 4 azeotropes. In the previous class, I had given a detailed demonstration as to how to read these ternary graphs. So if there is a doubt, you can reach out to me regarding any doubts for these ternary diagrams. And over here you can see the azeotropes that are being formed. So one azeotrope is given at this particular temperature, at this particular uh, concentration of 0.45 ethanol. And what is the composition of this particular azeotrope? Can anyone tell me? First, tell me whether it's a binary azeotrope or a ternary azeotrope.
Binary azeotrope, sir.
And what is the concentration of the 3 components?
Ethanol is 0.45, sir, and water is 0.55, sir.
Right. Next, what we have to do is we have to residual curves are there. Okay. So we are going to go to home. Next, we are going to select the residue curves. So we are going to continue to Aspen plus residue curves. So over here, the system is given. The number of curves are 10 to 15. And the pressure, I'm going to set it as 1 atmosphere. And we are going to run the analysis. So this is the residue curve map for the given system. I hope you all know what residue curves are. So if you are particularly starting from this concentration, then this is the given trajectory that you have to follow for separation. Is there any doubt? Fine. The last one is on regression. So we have to perform evaluation and regression on NIST vapor liquid equilibrium data of acetone MTBE system via regression tool, and we have to use Wilson method. We have done multiple problems on regression. So this is the last problem that I'm going to discuss on regression for this course. So it actually states us the utility as to why regression is needed and why is it beneficial. So what are the components that we have? We have acetone and MTB. So acetone, next is ethyl, ether. So we have specified both the components. Next, we are going to select the Wilson property method. We're going to click on next. Now, usually in a particular thermodynamic property method, if you go to Wilson and search over here, okay. So in this Aspen Wilson activity coefficient model, this is the gamma I that is being calculated for the Wilson model. This is the activity coefficient gamma I for the Wilson model, and it is calculated from this Aij values, Aij and Aji, where I and J are the components and Aij is the interaction parameter. And how do we calculate Aij? We calculate Aij from this correlation over here. If you see at this correlation over here, there are a total of five parameters that are required, and the interaction parameter of Aij, Bij, Cij, Dij, and Eij. And since there are two components, so there will be a total of 10 parameters that needs to be evaluated for the proper estimation of this Winsor activity coefficient model. Now, if you see this particular line over here, the data Aij, Bij, Cij, Dij, and Eij are unsymmetrical, which signifies that these are not equal to each other. That is, Aij will not be equal to Aji. In order to understand this in a simple term, Aij, if I is acetone and J is MTB, I think those are the two components that we are handling. Yes. So if I is acetone and J is MTB, then Aij is the interaction of acetone with MTB, while Aji is the interaction of MTB with acetone. Okay. Similarly, same definition stands for Bij, Cij, Dij, and Eij also. Now, from the Aspen property data bank, if you see, then the parameters that are required for the evaluation of Wilson coefficient model, out of 10 parameters, only 2 parameters are given over here. The rest of the parameters are given as 0. Only the T lower and T upper, that is the temperature range, is given to us. We don't have all these values to evaluate the parameters. So this actually is a problem, because this will add what should I say, this will add the calculations that we will be performing using this thermodynamic property method will be inaccurate, since all the property methods are not properly mentioned in the data that was retrieved from this source over here. So in this case, we have to use regression. Okay. So for that, what we have to do, we have to select regression initially. We have to select new, that is, no, for first, what we have to do is we have to retrieve the data. So what we are going to do, we are going to retrieve the binary mixture data for acetone and MTB. So we are retrieving the data for this. So here you can see that there is only one binary vapor liquid equilibrium data that is available for acetone and MTB. We are going to save this data. We are going to use this data for our regression analysis. So for this data, if we do the plot the TXY, then we are getting a graph like this. This is for experimental. And this is the notation of the graph, that is BVL001. Now if we go to home, and from the property method that we have selected, Wilson, we have this property method. Let me select as next. Acetone. Let us do the binary analysis using this data over here. So we are going to plot the TXY graph, and the pressure is 1.01325. But for the pressure of the experimental data was in 94 kilopascal, right? So let me just change it to 94 kilopascal and let me just run the analysis. So this is the graph that we are getting, and the temperature is in degrees Celsius. Now what we are going to do is we are going to derive the binary mixture for acetone and MTBE. And over here we have this data. The temperature is in Kelvin and the pressure you can see is in 94,000 Newton per meter square, that is 94,000 Pascal on 94 kilopascal. I'm going to save this data. Okay. Now, if I want to generate the graph of this TXY, so this is the graph that we are getting. So this is the graph which we have got for the initial, that is the from the interaction parameters that were retrieved from Aspen, and this is for the experimental data graph that we have got. Now if we merge these two plots, you can see, and with y-axis map, single y-axis, okay, then there is a considerable difference between the experimental data and the one that we have got from the Aspen. This is the Aspen data that we have got, and this is the experimental data point. So there is a considerable gap in this. So in order to have a proper fit, what we are going to do is we are going to do the regression of this data. And the reason why this deviation is existing is because we don't have these parameter values over here. The parameter values over here are set to 0. So that is why there is so much deviation that is taking place. So we are going to use this data over here, that is this experimental data, in order to have a proper, to update the parameter values of the Wilson model. So we are going to go to home and we are going to select regression. We are going to do a new regression. So as I have told previously, before doing regression we need to do evaluation. So the data set that we are going to do is for this. We are going to do for the consistency test. Let the tolerance be 5% and let us run. So the results are available. You can check the results over here. So here the consistency test, you can see that it has passed with a tolerance of 5%. The value that you have got is approximately around 4%, around 2.5% tolerance that you have achieved. So now what we are going to do is we are going to perform regression of this data set. So for that we need to specify the parameters. Note that we only have 2 parameters but we need 10. So what we are going to do is we are going to specify the type of parameter as the binary parameter. The name of the method is Wilson. The element is going to be 1. The component is acetone and the group is MTB. Okay. We just need to copy this column and paste it over here. One, two, three, four, and this is the 5th. Now this element interaction is going to change. So 2, 3, 4 and 5. So we have total 5 interaction parameters for acetone and MTB. So you just need to fill this This is for the Aij, Bij, Cij, Dij and Eij. This is Aij, Bij, Cij, Dij and Eij for acetone MTB interaction. Similarly, we are going to have 5 more interaction parameters for MTB and acetone. So we are going to select binary over here. This is going to be Wilson. In this case, this is element 1. This is going to be MTB and this is acetone. Note that since this model, the interaction parameters are unsymmetrical, the condition over here set AJI is equal to AIJ, we have set no. That is, both these parameters are not equal to each other. Next, we are going to copy paste this. So this is 1, 2, 3, 4 and 5. Okay. Now we are clicking on next. Okay. So we have to select acetone over here. Now you can see that the input is changed. We are going to click on next. So over here it is asking for run data regression cases. I'm going to click on OK. So the DR1 is there. We are going to click on OK. So the data regression is going to use this binary results from here. So if you go to the results, you can see that all the parameters have been updated. Previously you only had 2 parameters, but now you have all the parameters that are required. Okay, if you check the residual, it also has a very low residual over here, 0.52056. So now what we are going to do is we are going to update the parameters. So once we update the parameters and we select OK, so here is the old value that was there. This is the new values that we have obtained from regression. And now we are going to select OK. So if you come over here, you can see that all the values have been updated and the source is also changed now. Okay. Now what we are going to do is we are going to select next. Now we are going to do the binary analysis for the TXY acetone and MTB. The pressure that we are going to set is 94 kilopascal, and now we are going to run the analysis. We are going to keep the temperature as Kelvin. This is binary 2. Similarly, for this curve over here, we are going to generate a TXY. This is BVL001, and now we are going to merge the plots. Now if you put this into a single axis, click on OK, you can see that now the predicted values and the experimental model have are very close to each other, like they are exactly fitting with each other. Is there any doubt in this particular problem? Hello?
No, sir.
So with this, I would like to end the class. If there is a doubt or any concern for regarding any other topics, you can ask me. Else, I would end the class now. Okay then. Thank you everyone.
Thank you, sir.